Alright guys, in this section we're going to be discussing two important theorems, Rolle's theorem and the mean value theorem. In the previous section we saw that the extreme value theorem stated that a continuous function on a closed interval a to b must have both a minimum and a maximum on the interval. Both of these values, however, can occur at the endpoint. Now, Rolle's theorem gives conditions that guarantee the existence of an extreme value in the interior of the closed interval. So here we have Rolle's theorem. It says let f be continuous of a closed interval. Notice how this condition must be met before we can use the theorem. And differentiable on the open interval a to b. If f of a is equal to f of b, then there is at least one number c in the interval a to b such that the derivative of f at c is equal to 0. Showing this with a graph here, pretend we have a function here. For the sake of simplicity, we're going to have this sketch here, and this function is defined, is continuous and differentiable on this interval a to b, right? And this is a closed interval, so a and b are included. I'm just labeling here our function values. So we have a and b are different points on the x-coordinate, but they both map to the same function value. So in other words, f of a is equal to f of b. Now, for this picture, you can see how the peak right here, or the maximum of this function over this interval, is going to happen at, say, this c. And it is also differentiable because it's smooth, so the tangent line there is horizontal. Therefore, the slope of that tangent line will be equal to 0. In other words, f prime of c is equal to 0. So that's what this theorem is saying. It guarantees it. It guarantees that there is some number in between a and b, and let's say we call it c, such that the derivative of the function evaluated at this c is equal to 0. It's very important that you have a continuous function that is differentiable as well. This theorem is not going to be true if you don't have continuity and differentiability. Okay, so let's look at a quick application of Rolle's theorem. We have determined whether Rolle's theorem can be applied to f on the closed interval a to b. If Rolle's theorem can be applied, find all the values of c in the open interval a to b such that the derivative of f at c is equal to 0. If Rolle's theorem cannot be applied, explain why not. Remember the conditions of Rolle's theorem. We have to make sure that that happens before we can use it, so that we can determine whether it applies or not. We have a nice quadratic function here, which is polynomial. F of x is equal to negative x squared plus 3x. And notice how, just by the nature of a polynomial function, f is continuous and differentiable. Right away, we meet the conditions of Rolle's theorem, and then, of course, we're given a closed interval. The next part is to check that f of a is equal to f of b. Here, our a is the left endpoint, 0, and b is our right endpoint, which is 3. We evaluate f at 0 and f at 3 and plug that in, and we get both are equal to 0. So therefore, f of a is equal to f of b, where a is 0 and b is 3. All right, since all the conditions of Rolle's theorem are met, then we have that the Rolle's theorem does apply. So let's go ahead and find the c in between 0 and 3, some number between 0 and 3, where the derivative is equal to 0. Okay, we find the derivative first. That's a pretty straightforward calculation. Derivative of f would be equal to negative 2x plus 3. Set that equal to 0, and we get that x is equal to 3 halves. So then derivative is 0 at 3 halves, which is in between 0 and 3. So their c value is 3 halves. All right, here's another example. Okay, so where we have f of x is equal to x to the 2/3 minus 1, and our interval is negative 8 to 8. I'm going to go ahead and check that the function at the endpoints match. The function values of negative 8 at negative 8 and 8 are actually the same. That's part of the conditions of Rolle's theorem. Okay, and they do match. F of negative 8 is equal to 3. F of 8 is equal to 3. So therefore, f of a is equal to f of b, where a is negative 8 and b is 8. All right, finding the derivative of f, pretty straightforward. F prime of x would be equal to 2/3 x to the negative 1/3 minus 1. We can rewrite this as equal to 2/3 or 2 over 3 times cube root of x minus 1. Okay, so the reason I did the derivative first before I check continuity is because I wanted you to see how we can check continuity in the beginning. Actually, that's a condition, so we need to do that. But f is going to be continuous on this interval, -8 to 8, but is not differentiable everywhere on that interval. And you can see right away just by looking at the derivative that f prime of x is not defined at 0. So we have the cube root of x on the denominator there, and that's why I wrote it that way, so that you can clearly see that f prime of 0 does not exist. Therefore, Rolle's theorem does not apply. Right? Even though a lot of things, the conditions check out, but since f is not differentiable everywhere on that closed interval, then we'll not be able to use Rolle's theorem in here. Okay, the other theorem that we'll be discussing is the mean value theorem. And this is really just a generalization of Rolle's theorem. You can think of Rolle's theorem as a special case of the mean value theorem. Although the mean value theorem can be used directly in problem solving, just like we use Rolle's theorem, it is used more often to prove other theorems. Okay, in fact, we're going to use it or discuss it when we look at the fundamental theorem of calculus in a later section. All right, so here the idea of the mean value theorem is, remember how Rolle's theorem, this is kind of like the picture we had for when we were discussing Rolle's theorem, but in Rolle's theorem we had to have f of a be equal to f of b, where a and b were your endpoints on the closed interval. For the mean value theorem, we don't have to have that condition or that restriction. We could have a closed interval a to b where f of a does not have to be equal to f of b. And that's why I'm tracing this secant line through this graph, f. So we have our a and our b, and notice how we're going to have a c in between a and b, where the derivative or the slope of the tangent line of the function f at that c is going to be equal to the slope of that secant line that I have here in green. So if I label here my f of a, this point right there is fa, comma f of a, same thing for b, comma f of b, and remember, we don't have to have f of a equal to f of b. As a matter of fact, here they're different. If I write the slope of this secant line, the rise over run, difference of the y, divided by the difference of the x, you have f of b minus f of a divided by b over a. That is the slope of that secant line right there. Well, mean value theorem guarantees that there is some value c between a and b such that the derivative of f at that c is equal to that slope of the secant line. In other words, that quotient right there, f of b minus f of a over b minus a. So that is the mean value theorem. Okay, so here we have an example of how we can use the mean value theorem. We have very similar to the examples that we did for Rolle's theorem. We're going to determine whether the mean value theorem can be applied on f on this closed interval. If it can be applied, then we're going to find all the c's in the open interval a to b such that f prime of c is equal to that f of b minus f of a divided by b minus a. If the mean value theorem does not apply or cannot be applied, we're going to explain why not. Okay, we have the function here, sine of x, very familiar with this function, on the interval 0 to pi. And we already know from our trigonometry class that f is continuous, actually on all this domain, all reals. Since we're only looking at the function from 0 to pi, then it's continuous in that interval, and is also differentiable. These are just facts that we know from a previous course. Okay, so just like Rolle's theorem, we have to make sure that the function is continuous and differentiable at the given interval. Next, we're going to compute this, what we saw as the secant, the slope of the secant line, right? This quotient right there. Remember, a is 0 for us, b is pi. We don't need to check that f of a is equal to f of b. We just need to figure this out. This quotient right here. So plugging this into our function, we have that sine of pi minus sine of 0 is equal to pi minus 0. And we get that 0 minus 0 over pi is equal to 0. Okay, so since the function is continuous and is differentiable, we're going to go ahead and find the derivative of f, which is just cosine of x, and then set that equal to 0 and solve for x. So cosine of x equal to 0 goes down to 0 at pi halves. Since we're only interested in the solutions from 0 to pi, that's the only one here. Therefore, the mean value theorem does apply, right? Since f is continuous, is differentiable, we found that quotient to be equal to 0. So then mean value theorem is getting guaranteed that there is an x, there's some point between 0 and pi, which in our case is pi halves, where the derivative is equal to 0 as well. On the interval 0 to pi, c is equal to pi halves, and the derivative of f at pi halves is equal to 0, which is equal to that quotient. That's how we use the mean value theorem. All right, so one more example here. We have f of x equal to cosine of x plus tangent of x, and the same interval as before, 0 to pi. We're going to see if we can use mean value theorem in this particular problem. Right away, without going any further, we can see that f is not continuous everywhere in that interval, 0 to pi, and specifically at pi halves, x equal to pi halves, since tangent of pi halves is undefined. So then we know we're not going to have continuity there. Therefore, right away, we don't even need to compute the derivative or do anything else. The mean value theorem does not apply here, at least not on the interval 0 to pi.